Matter is made up of one or different type of elements. Under normal conditions, no other element exists as an independent atom in nature, except noble gases. However, a group of atoms is found to exist together as one species having characteristic properties. Such a group of atoms is called a molecule. Obviously, there must be some force which holds these constituent atoms together in the molecules. The attractive force which holds various constituents atoms, ions, etc. together in different chemical species is called a chemical bond. Since the formation of chemical compounds takes place as a result of combination of atoms of various elements in different ways, it raises many questions. Why do atoms combine? Why are only certain combinations possible? Why do some atoms combine while certain others do not? Why do molecules possess definite shapes? To answer such questions, different theories and concepts have been put forward from time to time. These are Kossel-Lewis approach, valence shell electron pair repulsion theory, valence bond theory, and molecular orbital theory. The evolution of various theories of valence and the interpretation of the nature of chemical bonds have closely been related to the developments in the understanding of the structure of atom, the electronic configuration of elements, and the periodic table. Every system tends to be more stable, and bonding is nature's way of lowering the energy of the system to attain stability. Kossel-Lewis approach to chemical bonding. In order to explain the formation of chemical bond in terms of electrons, a number of attempts were made, but it was only in 1916 when Kossel and Lewis succeeded independently in giving a satisfactory explanation. They were the first to provide some logical explanation of valence, which was based on the inertness of noble gases. Lewis pictured the atom in terms of a positively charged kernel, the nucleus plus the inner electrons, and the outer shell that could accommodate a maximum of 8 electrons. He further assumed that these 8 electrons occupy the corners of a cube which surround the kernel. Thus, the single outer shell electron of sodium would occupy one corner of the cube, while in the case of a noble gas, all the 8 corners would be occupied. This octet of electrons represents a particularly stable electronic arrangement. Lewis postulated that atoms achieve the stable octet when they are linked by chemical bonds. In the case of sodium and chlorine, this can happen by the transfer of an electron from sodium to chlorine, thereby giving the sodium plus and chlorine minus ions. In the case of other molecules like chlorine 2, hydrogen 2, fluorine 2, etc., the bond is formed by the sharing of a pair of electrons between the atoms. In the process, each atom attains a stable outer octet of electrons. Lewis symbols. In the formation of a molecule, only the outer shell electrons take part in chemical combination, and they are known as valence electrons. The inner shell electrons are well protected and are generally not involved in the combination process. G.N. Lewis, an American chemist, introduced simple notations to represent valence electrons in an atom. These notations are called Lewis symbols. Significance of Lewis symbols. The number of dots around the symbol represents the number of valence electrons. This number of valence electrons helps to calculate the common or group valence of the element. The group valence of the elements is generally either equal to the number of dots in Lewis symbols or 8 minus the number of dots or valence electrons. Kossel, in relation to chemical bonding, drew attention to the following facts. In the periodic table, the highly electronegative halogens and the highly electropositive alkali metals are separated by the noble gases. The formation of a negative ion from a halogen atom and a positive ion from an alkali metal atom is associated with the gain and loss of an electron by the respective atoms. The negative and positive ions are stabilized by electrostatic attraction. The bond formed as a result of the electrostatic attraction between the positive and negative ions, was termed as the electrovalent bond. The electrovalence is thus equal to the number of unit charge S on the ion. Thus, calcium is assigned a positive electrovalence of 2, while chlorine a negative electrovalence of 1. Kossel's postulations provide the basis for the modern concepts regarding ion formation by electron transfer and the formation of ionic crystalline compounds. His views have proved to be of great value in the understanding and systematization of the ionic compounds. At the same time, he did recognize the fact that a large number of compounds did not fit into these concepts. Octet rule. Kossel and Lewis in 1916 developed an important theory of chemical combination between atoms known as electronic theory of chemical bonding. According to this, atoms can combine either by transfer of valence electrons from one atom to another gaining or losing, or by sharing of valence electrons in order to have an octet in their valence shells. This is known as octet rule. Covalent bond. Lamier in 1919 refined the Lewis postulations by abandoning the idea of the stationary cubical arrangement of the octet and by introducing the term covalent bond. The Lewis-Lamier theory can be understood by considering the formation of the chlorine molecule. The formation of the chlorine gas molecule can be understood in terms of the sharing of a pair of electrons between the two chlorine atoms, each chlorine atom contributing one electron to the shared pair. In the process, both chlorine atoms attain the outer shell octet of the nearest noble gas, that is argon. The dots represent electrons. Such structures are referred to as Lewis dot structures. The Lewis dot structures can be written for other molecules also, in which the combining atoms may be identical or different. The important conditions being that each bond is formed as a result of sharing of an electron pair between the atoms. Each combining atom contributes at least one electron to the shared pair. The combining atoms attain the outer shell noble gas configurations as a result of the sharing of electrons. When two atoms share one electron pair, they are said to be joined by a single covalent bond. In many compounds, we have multiple bonds between atoms. The formation of multiple bonds envisages sharing of more than one electron pair between two atoms. If two atoms share two pairs of electrons, the covalent bond between them is called a double bond. For example, in the carbon dioxide molecule, we have two double bonds between the carbon and oxygen atoms. Similarly, in ethene molecule, the two carbon atoms are joined by a double bond. Chemical bonding and molecular structure. When combining atoms share three electron pairs, as in the case of two nitrogen atoms in the nitrogen 2 molecule and the two carbon atoms in the ethene molecule, a triple bond is formed. Lewis representation of simple molecules, the Lewis structures. The Lewis structures provide a picture of bonding in molecules and ions in terms of the shared pairs of electrons and the octet rule. While such a picture may not explain the bonding and behavior of a molecule completely, it does help in understanding the formation and properties of a molecule to a large extent. Writing of Lewis structures of molecules is, therefore, very useful. The total number of electrons required for writing the structures are obtained by adding the valence electrons of the combining atoms. For example, in the chlorine-hydrogen 4 molecule, there are 8 valence electrons available for bonding 4 from carbon and 4 from the 4 hydrogen atoms. For anions, each negative charge would mean addition of 1 electron. For cations, each positive charge would result in subtraction of 1 electron from the total number of valence electrons. For example, for the carbonate ion, the 2 negative charges indicate that there are 2 additional electrons than those provided by the neutral atoms. For ammonium ion, 1 positive charge indicates the loss of 1 electron from the group of neutral atoms. Knowing the chemical symbols of the combining atoms and having knowledge of the skeletal structure of the compound known or guessed intelligently, it is easy to distribute the total number of electrons as bonding shared pairs between the atoms in proportion to the total bonds. In general, the least electronegative atom occupies the central position in the molecule/ion. For example, in the nitrogen trifluoride and carbonate, nitrogen and carbon are the central atoms, whereas fluorine and oxygen occupy the terminal positions. After accounting for the shared pairs of electrons for single bonds, the remaining electron pairs are either utilized for multiple bonding or remain as the lone pairs. The basic requirement being that each bonded atom gets an octet of electrons. Formal charge, Lewis dot structures, in general, do not represent the actual shapes of the molecules. In case of polyatomic ions, the net charge is possessed by the ion as a whole and not by a particular atom. It is, however, feasible to assign a formal charge on each atom. The formal charge of an atom in a polyatomic molecule, or ion, may be defined as the difference between the number of valence electrons of that atom in an isolated or free state and the number of electrons assigned to that atom in the Lewis structure. The counting is based on the assumption that the atom in the molecule owns one electron of each shared pair and both the electrons of a lone pair. We must understand that formal charges do not indicate real charge separation within a molecule. Indicating the charges on the atoms in the Lewis structure only helps in keeping track of the valence electrons in the molecule. Formal charges help in the selection of the lowest energy structure from a number of possible Lewis structures for a given species. Generally, the lowest energy structure is the one with the smallest formal charges on the atoms. The formal charge is a factor based on a pure covalent view of bonding in which electron pairs are shared equally by neighboring atoms. Limitations of the octet rule. The octet rule, though useful, is not universal. It is quite useful for understanding the structures of most of the organic compounds, and it applies mainly to the second period elements of the periodic table. There are three types of exceptions to the octet rule. The incomplete octet of the central atom. In some compounds, the number of electrons surrounding the central atom is less than 8. This is especially the case with elements having less than 4 valence electrons. Odd electron molecules. In molecules with an odd number of electrons like nitric oxide, and nitrogen dioxide, the octet rule is not satisfied for all the atoms. The expanded octet. Elements in and beyond the third period of the periodic table have, apart from 3s and 3p orbitals, 3d orbitals also available for bonding. In a number of compounds of these elements, there are more than 8 valence electrons around the central atom. This is termed as the expanded octet. Obviously, the octet rule does not apply in such cases. Interestingly, sulfur also forms many compounds in which the octet rule is obeyed. In sulfur dichloride, the S atom has an octet of electrons around it. Other drawbacks of the octet theory. It is clear that octet rule is based upon the chemical inertness of noble gases. However, some noble gases, for example xenon and krypton, also combine with oxygen and fluorine to form a number of compounds like xenon difluoride, krypton difluoride, xenon oxide, difluoride, etc. This theory does not account for the shape of molecules. It does not explain the relative stability of the molecules being totally silent about the energy of a molecule. Ionic or electrovalent bond. From the Kossel and Lewis treatment of the formation of an ionic bond, it follows that the formation of ionic compounds would primarily depend upon the ease of formation of the positive and negative ions from the respective neutral atoms, the arrangement of the positive and negative ions in the solid, that is, the lattice of the crystalline compound. The formation of a positive ion involves ionization, that is, removal of electron from the neutral atom, and that of the negative ion involves the addition of electron to the neutral atom. The electron gain enthalpy when a gas phase atom in its ground state gains an electron. The electron gain process may be exothermic or endothermic. The ionization, on the other hand, is always endothermic. Electron affinity is the negative of the energy change accompanying electron gain. Obviously, ionic bonds will be formed more easily between elements with comparatively low ionization enthalpies and elements with comparatively high negative value of electron gain enthalpy. Most ionic compounds have cations derived from metallic elements and anions from nonmetallic elements. The ammonium ion, made up of two nonmetallic elements, is an exception. It forms the cation of a number of ionic compounds. Ionic compounds in the crystalline state consist of orderly three-dimensional arrangements of cations and anions held together by Coulombic interaction energies. These compounds crystallize in different crystal structures determined by the size of the ions, their packing arrangements, and other factors. The crystal structure of sodium chloride, NaCl rock salt. In ionic solids, the sum of the electron gain enthalpy and the ionization enthalpy may be positive, but still the crystal structure gets stabilized due to the energy released in the formation of the crystal lattice. Thus, a qualitative measure of the stability of an ionic compound is provided by its enthalpy of lattice formation and not simply by achieving octet of electrons around the ionic species in gaseous state. Since lattice enthalpy plays a key role in the formation of ionic compounds, it is important that we learn more about it. Lattice enthalpy. The lattice enthalpy of an ionic solid is defined as the energy required to completely separate 1 mole of a solid ionic compound into gaseous constituent ions. This process involves both the attractive forces between ions of opposite charges and the repulsive forces between ions of like charge. The solid crystal being three-dimensional, it is not possible to calculate lattice enthalpy directly from the interaction of forces of attraction and repulsion only. Factors associated with the crystal geometry have to be included. Bond parameters, bond length. Bond length is defined as the equilibrium distance between the nuclei of two bonded atoms and molecule. Bond lengths are measured by spectroscopic, X-ray diffraction, and electron diffraction techniques about which you will learn in higher classes. In the case of a covalent bond, the contribution from each atom is called the covalent radius of that atom. The covalent radius is measured approximately as the radius of an atom's core, which is in contact with the core of an adjacent atom in a bonded situation. The covalent radius is half of the distance between two similar atoms joined by a covalent bond in the same molecule. The van der Waals radius represents the overall size of the atom, which includes its valence shell in a non-bonded situation. Further, the van der Waals radius is half of the distance between two similar atoms in separate molecules in a solid. Bond angle, it is defined as the angle between the orbitals containing bonding electron pairs around the central atom in a molecule/complex ion. Bond angle is expressed in degree, which can be experimentally determined by spectroscopic methods. It gives some idea regarding the distribution of orbitals around the central atom in a molecule/complex ion, and hence it helps us in determining its shape. Bond enthalpy. It is defined as the amount of energy required to break 1 mole of bonds of a particular type between two atoms in a gaseous state. The unit of bond enthalpy is kilojoules per mole. Similarly, the bond enthalpy for molecules containing multiple bonds. It is important that larger the bond dissociation enthalpy, stronger will be the bond in the molecule. In case of polyatomic molecules, the measurement of bond strength is more complicated. Bond order. In the Lewis description of covalent bond, The bond order is given by the number of bonds between the two atoms in a molecule. The bond order, for example, in hydrogen with a single shared electron pair, in oxygen with two shared electron pairs, and in nitrogen with three shared electron pairs is 1, 2, 3 respectively. Similarly, in carbon monoxide, three shared electron pairs between carbon and oxygen, the bond order is 3. For nitrogen, bond order is 3 and it is 946 kilojoules per mole, being one of the highest for a diatomic molecule. Isoelectronic molecules and ions have identical bond orders. A genera L correlation useful for understanding the stabilities of molecules is that, with increase in bond order, bond enthalpy increases and bond length decreases. Resonance structures. IDIS often observed that a single Lewis structure is inadequate for the representation of a molecule in conformity with its experimentally determined parameters. Experimentally determined oxygen-oxygen bond lengths in the ozone molecule are same 128 pm. Thus, the oxygen-oxygen bonds in the ozone molecule are intermediate between a double and a single bond. Obviously, this cannot be represented by either of the two Lewis structures shown above. The concept of resonance was introduced to deal with the type of difficulty experienced in the depiction of accurate structures of molecules like ozone. According to the concept of resonance, whenever a single Lewis structure cannot describe a molecule accurately, a number of structures with similar energy, positions of nuclei, bonding and non-bonding pairs of electrons are taken as the canonical structures of the hybrid, which describes the molecule accurately. Thus, for ozone, the two structures shown above constitute the canonical structures or resonance structures in their hybrid. This is also called resonance hybrid. Resonance is represented by a double-headed arrow. Some of the other examples of resonance structures are provided by the carbonate ion and the carbon dioxide molecule. In general, it may be stated that resonance stabilizes the molecule as the energy of the resonance hybrid is less than the energy of any single canonical structure, and resonance averages the bond characteristics as a whole. Many misconceptions are associated with resonance, and the same need to be dispelled. You should remember that the canonical forms have no real existence. The molecule does not exist for a certain fraction of time in one canonical form and for other fractions of time in other canonical forms. There is no such equilibrium between the canonical forms as we have between tautomeric forms keto and enol in tautomerism. The molecule as such has a single structure, which is the resonance hybrid of the canonical forms, and which cannot as such be depicted by a single Lewis structure. Polarity of bonds. The existence of 100% ionic or covalent bond represents an ideal situation. In reality, no bond or a compound is either completely covalent or ionic. Even in case of covalent bond between two hydrogen atoms, there is some ionic character. When covalent bond is formed between two similar atoms, for example in hydrogen, oxygen, carbon L2, nitrogen, or fluorine gas, the shared pair of electrons is equally attracted by the two atoms. As a result, electron pair is situated exactly between the two identical nuclei. The bond so formed is called nonpolar covalent bond. Contrary to this, in case of a heteronuclear molecule like HF, the shared electron pair between the two atoms gets displaced more towards fluorine, since the electronegativity of fluorine unit 3 is far greater than that of hydrogen. The resultant covalent bond is a polar covalent bond. As a result of polarization, the molecule possesses the dipole moment depicted below, which can be defined as the product of the magnitude of the charge and the distance between the centers of positive and negative charge. It is usually designated by a Greek letter. Mathematically, it is expressed as follows: dipole moment equal to charge q multiplied by distance of separation r. Dipole moment is usually expressed in debye units d. The conversion factor is one dipole equal to 3.33564 multiply by 10 power minus 30 coulometer. Further dipole moment is a vector quantity, and by convention, it is depicted by a small arrow with tail on the negative center and head pointing towards the positive center. But in chemistry, presence of dipole moment is represented by the crossed arrow put on Lewis structure of the molecule. The cross is on positive end and arrowhead is on negative end. Note that the direction of crossed arrow is opposite to the conventional direction of dipole moment vector. In case of polyatomic molecules, the dipole moment not only depend upon the individual dipole moments of bonds known as bond dipoles, but also on the spatial arrangement of various bonds in the molecule. In such case, the dipole moment of a molecule is the vector sum of the dipole moments of various bonds. The dipole moment in case of beryllium fluoride is 0. This is because the two equal bond dipoles point in opposite directions and cancel the effect of each other. Let us study an interesting case of ammonia and nitrogen trifluoride molecule. Both the molecules have pyramidal shape with a lone pair of electrons on nitrogen atom. Although fluorine is more electronegative than nitrogen, the resultant dipole moment of ammonia 4.90 multiply by 10 power minus 30 coulometer is greater than that of nitrogen trifluoride 0.8 multiply by 10 power minus 30 coulometer. This is because, in case of ammonia, the orbital dipole due to lone pair is in the same direction as the resultant dipole moment of the nitrogen-hydrogen bonds. Whereas in nitrogen trifluoride, the orbital dipole is in the direction opposite to the resultant dipole moment of the three nitrogen-fluorine bonds. The orbital dipole, because of lone pair, decreases the effect of the resultant nitrogen-fluorine bond moments. Just as all the covalent bonds have some partial ionic character, the ionic bonds also have partial covalent character. The smaller the size of the cation and the larger the size of the anion, the greater the covalent character of an ionic bond. The greater the charge on the cation, the greater the covalent character of the ionic bond. For cations of the same size and charge, the one, with electronic configuration typical of transition metals, is more polarizing than the one with a noble gas configuration. S orbital is fully filled with 2 electrons. Full, completely filled p subshell, typical of alkali and alkaline earth metal cations. The cation polarizes the anion, pulling the electronic charge toward itself and thereby increasing the electronic charge between the two. This is precisely what happens in a covalent bond, that is buildup of electron charge density between the nuclei. The polarizing power of the cation, the polarizability of the anion, and the extent of distortion polarization of anion are the factors which determine the percent covalent character of the ionic bond. The valence shell electron pair repulsion theory. As already explained, Lewis' concept is unable to explain the shapes of molecules. This theory provides a simple procedure to predict the shapes of covalent molecules. Sidgwick and Powell in 1940 proposed a simple theory based on the repulsive interactions of the electron pairs in the valence shell of the atoms. It was further developed and redefined by Nyholm and Gillespie, 1957. The main postulates of valence shell electron pair repulsion theory are as follows. The shape of the molecule depends upon the number of valence shell electron pairs bonded or non-bonded around the central atom. Pairs of electrons in the valence shell repel one another since their electron clouds are negatively charged. These pairs of electrons tend to occupy such positions in space that minimize repulsion and thus maximize distance between them. The valence shell is taken as a sphere with the electron pairs localizing on the spherical surface at maximum distance from one another. A multiple bond is treated as if it is a single electron pair, and the 2 or 3 electron pairs of a multiple bond are treated as a single superpair. Where 2 or more resonance structures can represent a molecule, the valence shell electron pair repulsion model is applicable to any such structure. The repulsive interaction of electron pairs decrease in the order. Nyholm and Gillespie 1957 refined the valence shell electron pair repulsion model by explaining the important difference between the lone pairs and bonding pairs of electrons. While the lone pairs are localized on the central atom, each bonded pair is shared between 2 atoms. As a result, the lone pair electrons in a molecule occupy more space as compared to the bonding pairs of electrons. This results in greater repulsion between lone pairs of electrons as compared to the lone pair, and bond pair repulsions. These repulsion effects result in deviations from idealized shapes and alterations in bond angles in molecules. For the prediction of geometrical shapes of molecules with the help of valence shell electron pair repulsion theory, it is convenient to divide molecules into 2 categories as one. Molecules in which the central atom has no lone pair and 2. Molecules in which the central atom has 1 or more lone pairs. The valence shell electron pair repulsion theory is able to predict geometry of a large number of molecules, especially the compounds of p-block elements, accurately. It is also quite successful in determining the geometry quite accurately even when the energy difference between possible structures is very small. The theoretical basis of the valence shell electron pair repulsion theory regarding the effects of electron pair repulsions on molecular shapes is not clear and continues to be a subject of doubt and discussion. Valence bond theory. As we know that Lewis approach helps in writing the structure of molecules, but it fails to explain the formation of chemical bond. It also does not give any reason for the difference in bond dissociation enthalpies and bond lengths in molecules like hydrogen 435.8 kilojoules per mole, 74 picometer, and fluorine gas 155 kilojoules per mole, 144 picometer. Although in both the cases a single covalent bond is formed by the sharing of an electron pair between the respective atoms. It also gives no idea about the shapes of polyatomic molecules. Similarly, the valence shell electron pair repulsion theory gives the geometry of simple molecules, but theoretically, it does not explain them, and also it has limited applications. To overcome these limitations, the 2 important theories based on quantum mechanical principles are introduced. These are valence bond theory and molecular orbital theory. Valence bond theory was introduced by Heitler in London 1927 and developed further by Pauling and others. A discussion of the valence bond theory is based on the knowledge of atomic orbitals, electronic configurations of elements, the overlap criteria of atomic orbitals, the hybridization of atomic orbitals, and the principles of variation and superposition. A rigorous treatment of the valence bond theory in terms of these aspects is beyond the scope of this book. Therefore, for the sake of convenience, valence bond theory has been discussed in terms of qualitative and non-mathematical treatment only. To start with, let us consider the formation of hydrogen molecule, which is the simplest of all molecules. Consider 2 hydrogen atoms A and B approaching each other, having nuclei A and B, and electrons present in them are represented by electron A and electron B. When the 2 atoms are at large distance from each other, there is no interaction between them. As these 2 atoms approach each other, new attractive and repulsive forces begin to operate. Attractive forces arise between nucleus of one atom and its own electron, that is nucleus A attracting electron A and nucleus B attracting electron B. Nucleus of one atom and electron of other atom, that is a nucleus with B electron, B nucleus with A electron. Similarly, repulsive forces arise between electrons of 2 atoms like electron A with electron B, nuclei of two atoms, nucleus A with nucleus B. Attractive forces tend to bring the two atoms close to each other, whereas repulsive forces tend to push them. Experimentally, it has been found that the magnitude of new attractive force is more than the new repulsive forces. As a result, two atoms approach each other and potential energy decreases. Ultimately, a stage is reached where the net force of attraction balances the force of repulsion and system acquires minimum energy. At this stage, two hydrogen atoms are said to be bonded together to form a stable molecule having the bond length of 74 picometer. Since the energy gets released when the bond is formed between two hydrogen atoms, the hydrogen molecule is more stable than that of isolated hydrogen atoms. The energy so released is called as bond enthalpy. Orbital overlap concept. In the formation of hydrogen molecule, there is a minimum energy state when two hydrogen atoms are so near that their atomic orbitals undergo partial interpenetration. This partial merging of atomic orbitals is called overlapping of atomic orbitals, which results in the pairing of electrons. The extent of overlap decides the strength of a covalent bond. In general, greater the overlap, the stronger is the bond formed between two atoms. Therefore, according to orbital overlap concept, the formation of a covalent bond between two atoms results by pairing of electrons present in the valence shell having opposite spins. Directional properties of bonds. As we have already seen, the covalent bond is formed by overlapping of atomic orbitals. The molecule of hydrogen is formed due to the overlap of one's orbitals of two hydrogen atoms. In case of polyatomic molecules like methane, ammonia, and water, the geometry of the molecules is also important in addition to the bond formation. For example, why is it so that methane molecule has tetrahedral shape and hexachlorocyclohexane bond angles are 109.5 degrees? Why is the shape of ammonia molecule pyramidal? The valence bond theory explains the shape, the formation, and directional properties of bonds in polyatomic molecules like methane, ammonia, and water, etc., in terms of overlap and hybridization of atomic orbitals. Overlapping of atomic orbitals. When orbitals of two atoms come close to form bond, their overlap may be positive, negative, or zero, depending upon the sign phase and direction of orientation of amplitude of orbital wave function in space. Orbitals forming bond should have same sign phase and orientation in space. This is called positive overlap. Various overlaps of s and p orbitals are depicted. The criterion of overlap as the main factor for the formation of covalent bonds applies uniformly to the homonuclear/heteronuclear diatomic molecules and polyatomic molecules. We know that the shapes of methane, ammonia, and water molecules are tetrahedral, pyramidal, and bent respectively. It would be therefore interesting to use valence bond theory to find out if these geometrical shapes can be explained in terms of the orbital overlaps. Let's first consider the methane molecule. The energy required for this excitation is compensated by the release of energy due to overlap between the orbitals of carbon and the hydrogen. The four atomic orbitals of carbon, each with an unpaired electron, can overlap with the one's orbitals of the four hydrogen atoms, which are also singly occupied. This will result in the formation of four carbon-hydrogen bonds. It will, however, be observed that while the 3p orbitals of carbon are at 90 degrees to one another, the HCH angle for these will also be 90 degrees. That is, three carbon-hydrogen bonds will be oriented at 90 degrees to one another. The 2's orbital of carbon and the 1's orbital of hydrogen are spherically symmetrical and they can overlap in any direction. Therefore, the direction of the fourth carbon-hydrogen bond cannot be ascertained. This description does not fit in with the tetrahedral hexachlorocyclohexane angles of 109.5 degrees. Clearly, it follows that simple atomic orbital overlap does not account for the directional characteristics of bonds in methane. Using similar procedure and arguments, it can be seen that in the case of ammonia and water molecules, the hydrogen-nitrogen-hydrogen and hydrogen-oxygen-hydrogen angles should be 90 degrees. This is in disagreement with the actual bond angles of 107 degree and 104.5 degree in the ammonia and water molecules respectively. Types of overlapping and nature of covalent bonds. The covalent bond may be classified into two types depending upon the types of overlapping, sigma bond and pi bond. Sigma bond. This type of covalent bond is formed by the end-to-end head-on overlap of bonding orbitals along the internuclear axis. This is called as head-on overlap or axial overlap. This can be formed by any one of the following types of combinations of atomic orbitals. SS overlapping. In this case, there is overlap of two half-filled s orbitals along the internuclear. sp overlapping. This type of overlap occurs between half-filled s orbitals of one atom and half-filled p orbitals of another atom. p overlapping. This type of overlap takes place between half-filled p orbitals of the two approaching atoms. Pi bond. In the formation of pi bond, the atomic orbitals overlap in such a way that their axes remain parallel to each other and perpendicular to the internuclear axis. The orbitals formed due to sidewise overlapping consists of two saucer-type charge cloud strength of sigma and pi bonds. Basically, the strength of a bond depends upon the extent of overlapping. In case of sigma bond, the overlapping of orbitals takes place to a larger extent. Hence, it is stronger as compared to the pi bond where the extent of overlapping occurs to a smaller extent. Further, it is important to note that in the formation of multiple bonds between two atoms of a molecule, pi bond S is formed in addition to a sigma bond. The phenomenon is known as hybridization, which can be defined as the process of intermixing of the orbitals of slightly different energies so as to redistribute their energies, resulting in the formation of new set of orbitals of equivalent energies and shape. For example, when 1,2s and 3,2p orbitals of carbon hybridize, there is the formation of 4 new sp, 3 hybrid orbitals. Salient features of hybridization. The main features of hybridization are as under. The number of hybrid orbitals is equal to the number of the atomic orbitals that get hybridized. The hybridized orbitals are always equivalent in energy and shape. The hybrid orbitals are more effective in forming stable bonds than the pure atomic orbitals. These hybrid orbitals are directed in space in some preferred direction to have minimum repulsion between electron pairs and thus a stable arrangement. Therefore, the type of hybridization indicates the geometry of the molecules. Important conditions for hybridization: the orbitals present in the valence shell of the atom are hybridized. The orbitals undergoing hybridization should have almost equal energy. Promotion of electron is not essential condition prior to hybridization. It is not necessary that only half-filled orbitals participate in hybridization. In some cases, even filled orbitals of valence shell take part in hybridization. Types of hybridization. There are various types of hybridization involving s, p, and d orbitals. The different types of hybridization are as under. sp hybridization. This type of hybridization involves the mixing of one s and one p orbital, resulting in the formation of two equivalent sp hybrid orbitals. The suitable orbitals for sp hybridization are s and pz, if the hybrid orbitals are to lie along the z-axis. Each sp hybrid orbitals has 50% s character and 50% p character. Such a molecule in which the central atom is sp hybridized and linked directly to two other central atoms possesses linear geometry. This type of hybridization is also known as diagonal hybridization. The two sp hybrids point in the opposite direction along the z-axis with projecting positive lobes and very small negative lobes, which provides more effective overlapping, resulting in the formation of stronger bonds. sp2 hybridization. In this hybridization, there is involvement of one s and two p orbitals in order to form three equivalent sp2 hybridized orbitals. sp3 hybridization. This type of hybridization can be explained by taking the example of methane molecule, in which there is mixing of 1s orbital and 3p orbitals of the valence shell to form 4sp, 3 hybrid orbital of equivalent energies and shape. There is 25 degree s character and 75 degree p character in each sp3 hybrid orbital. The 4 sp3 hybrid orbitals so formed are directed towards the four corners of the tetrahedron. The structure of ammonia and water molecules can also be explained with the help of sp3 hybridization. These three hybrid orbitals overlap with 1s orbitals of hydrogen atoms to form three nitrogen-hydrogen sigma bonds. We know that the force of repulsion between a lone pair and a bond pair is more than the force of repulsion between two bond pairs of electrons. The molecule thus gets distorted and the bond angle is reduced to 107 degree from 109.5 degree. In case of H2O molecule, the four oxygen orbitals 1 2s and 3 2p undergo sp3 hybridization, forming 4sp, 3 hybrid orbitals, out of which 2 contain 1 electron each and the other 2 contain a pair of electrons. These 4 sp3 hybrid orbitals acquire a tetrahedral geometry, with 2 corners occupied by hydrogen atoms while the other 2 by the lone pairs. Hybridization of elements involving d orbitals. The elements present in the third period contain d orbitals in addition to s and p orbitals. The energy of the 3d orbitals are comparable to the energy of the 3s and 3p orbitals. The energy of 3d orbitals are also comparable to those of 4s and 4p orbitals. As a consequence, the hybridization involving either 3s, 3p and 3d, or 3d, 4s and 4p is possible. However, since the difference in energies of 3p and 4s orbitals is significant, no hybridization involving 3p, 3d, and 4s orbitals is possible. Molecular orbital theory. Molecular orbital (MO) theory was developed by F. Hund and R.S. Mulliken in 1932. The salient features of this theory are: the electrons in a molecule are present in the various molecular orbitals, as the electrons of atoms are present in the various atomic orbitals. The atomic orbitals of comparable energies and proper symmetry combine to form molecular orbitals. While an electron in an atomic orbital is influenced by one nucleus, in a molecular orbital it is influenced by two or more nuclei, depending upon the number of atoms in the molecule. Thus, an atomic orbital is monocentric while a molecular orbital is polycentric. The number of molecular orbital formed is equal to the number of combining atomic orbitals. When two atomic orbitals combine, two molecular orbitals are formed. One is known as bonding molecular orbital, while the other is called anti-bonding molecular orbital. The bonding molecular orbital has lower energy and hence greater stability than the corresponding anti-bonding molecular orbital. Just as the electron probability distribution around a nucleus in an atom is given by an atomic orbital, the electron probability distribution around a group of nuclei in a molecule is given by a molecular orbital. The molecular orbitals, like atomic orbitals, are filled in accordance with the Aufbau principle, obeying the Pauli's exclusion principle and the Hund's rule. Formation of molecular orbitals, linear combination of atomic orbitals. According to wave mechanics, the atomic orbitals can be expressed by wave functions, which represent the amplitude of the electron waves. These are obtained from the solution of Schrödinger wave equation. However, since it cannot be solved for any system containing more than one electron, molecular orbitals, which are one-electron wave functions for molecules, are difficult to obtain directly from the solution of Schrödinger wave equation. To overcome this problem, an approximate method known as linear combination of atomic orbitals has been adopted. Let us apply this method to the homonuclear diatomic hydrogen molecule. Consider the hydrogen molecule consisting of two atoms, A and B. Each hydrogen atom in the ground state has one electron in one's orbital. The atomic orbitals of these atoms may be represented by the wave functions of an atomic orbital on atom A and B. Mathematically, the formation of molecular orbitals may be described by the linear combination of atomic orbitals that can take place by addition and by subtraction of wave functions of individual atomic orbitals, as shown below. Molecular orbital wave function equal to the wave function of an atomic orbital on atom plus the wave function of an atomic orbital on atom B. Therefore, the two molecular orbitals sigma molecular orbital and sigma anti-bonding orbital are formed as sigma molecular orbital equal to the wave function of an atomic orbital on atom plus the wave function of an atomic orbital on atom B. Sigma anti-bonding orbital equal to the wave function of an atomic orbital on atom minus the wave function of an atomic orbital on atom B. The molecular orbital sigma, molecular orbital formed by the addition of atomic orbitals, is called the bonding molecular orbital, while the molecular orbital sigma, anti-bonding orbital formed by the subtraction of atomic orbital, is called anti-bonding molecular orbital. Qualitatively, the formation of molecular orbitals can be understood in terms of the constructive or destructive interference of the electron waves of the combining atoms. In the formation of bonding molecular orbital, the two electron waves of the bonding atoms reinforce each other due to constructive interference, while in the formation of anti-bonding molecular orbital, the electron waves cancel each other due to destructive interference. As a result, the electron density in a bonding molecular orbital is located between the nuclei of the bonded atoms, because of which the repulsion between the nuclei is very less. While in case of an anti-bonding molecular orbital, most of the electron density is located away from the space between the nuclei. In fact, there's a nodal plane on which the electron density is zero between the nuclei, and hence the repulsion between the nuclei is high. Electrons placed in a bonding molecular orbital tend to hold the nuclei together and stabilize a molecule. In contrast, the electrons placed in the anti-bonding molecular orbital destabilize the molecule. This is because the mutual repulsion of the electrons in this orbital is more than the attraction between the electrons and the nuclei, which causes a net increase in energy. The total energy of two molecular orbitals, however, remains the same as that of two original atomic orbitals. Conditions for the combination of atomic orbitals. The linear combination of atomic orbitals to form molecular orbitals takes place only if the following conditions are satisfied. 1. The combining atomic orbitals must have the same or nearly the same energy. This means that one's orbital can combine with another one's orbital, but not with two's orbital, because the energy of two's orbital is appreciably higher than that of one's orbital. This is not true if the atoms are very different. 2. The combining atomic orbitals must have the same symmetry about the molecular axis. By convention, z-axis is taken as the molecular axis. It is important to note that atomic orbitals having same or nearly the same energy will not combine if they do not have the same symmetry. 3. The combining atomic orbitals must overlap to the maximum extent. The greater the extent of overlap, the greater will be the electron density between the nuclei of a molecular orbital. Types of molecular orbitals. Molecular orbitals of diatomic molecules are designated as sigma, pi, delta, etc. In this nomenclature, the sigma molecular orbitals are symmetrical around the bond axis, while pi molecular orbitals are not symmetrical. For example, the linear combination of 1's orbitals centered on 2 nuclei produces 2 molecular orbitals, which are symmetrical around the bond axis. Electronic configuration and molecular behavior. The distribution of electrons among various molecular orbitals is called the electronic configuration of a molecule. From the electronic configuration of a molecule, it is possible to get important information about the molecule, as discussed below. Stability of molecules. If number of electrons in bonding molecular orbitals is the number of electrons occupying bonding orbitals and the number occupying the anti-bonding orbitals, then the molecule is stable if number of electrons in bonding molecular orbitals is greater than number of electrons in anti-bonding molecular orbitals. And 2. The molecule is unstable if number of electrons in bonding molecular orbitals is less than number of electrons in anti-bonding molecular orbitals. In first, more bonding orbitals are occupied, and so the bonding influence is stronger and a stable molecule results. In second, the anti-bonding influence is stronger, and therefore the molecule is unstable. Bond order. Bond order is defined as 1/2 the difference between the number of electrons present in the bonding and the anti-bonding orbitals. The rules discussed above regarding the stability of the molecule can be restated in terms of bond order as follows. A positive bond order, that is number of electrons in bonding molecular orbitals greater than number of electrons in anti-bonding molecular orbitals, means a stable molecule. While a negative, that is number of electrons in bonding molecular orbitals smaller than number of electrons in anti-bonding molecular orbitals, or 0, that is number of electrons in bonding molecular orbitals equal to number of electrons in anti-bonding molecular orbitals. Bond order means an unstable molecule. Nature of the bond. Integral bond order values of 1, 2, or 3 correspond to single, double, or triple bonds respectively as studied in the classical concept. Bond length. The bond order between two atoms in a molecule may be taken as an approximate measure of the bond length. The bond length decreases as bond order increases. Magnetic nature. If all the molecular orbitals in a molecule are doubly occupied, the substance is diamagnetic, repelled by magnetic field. Bonding in some homonuclear diatomic molecules. In this section, we shall discuss bonding in some homonuclear diatomic molecules. 1. Hydrogen molecule. It is formed by the combination of two hydrogen atoms. Each hydrogen atom has one electron in one's orbital. Therefore, in all there are 2 electrons in hydrogen molecule, which are present in sigma, one's molecular orbital. 2. Helium molecule. The electronic configuration of helium atom is 1s2. Each helium atom contains 2 electrons. Therefore, in helium molecule, there would be 4 electrons. 3. Lithium molecule. The electronic configuration of lithium is 1s2, 2s1. There are 6 electrons in lithium molecule. 4. Carbon molecule. The electronic configuration of carbon is 1s2, 2s2, 2p2. There are 12 electrons in carbon molecule. 5. Oxygen molecule. The electronic configuration of oxygen atom is 1s2, 2s2, 2p4. Each oxygen atom has 8 electrons. Hence, in oxygen molecule, there are 16 electrons. Hydrogen bonding. Nitrogen, oxygen, and fluorine are the highly electronegative elements. When they are attached to a hydrogen atom to form covalent bond, the electrons of the covalent bond are shifted towards the more electronegative atom. This partially positively charged hydrogen atom forms a bond with the other more electronegative atom. This bond is known as hydrogen bond and is weaker than the covalent bond. Thus, hydrogen bond can be defined as the attractive force which binds hydrogen atom of one molecule with the electronegative atom of another molecule. Cause of formation of hydrogen bond. When hydrogen is bonded to strongly electronegative element X, the electron pair share between the two atoms moves far away from hydrogen atom. As a result, the hydrogen atom becomes highly electropositive with respect to the other atom X. Since there is displacement of electrons towards X, the hydrogen acquires fractional positive charge, while X attains fractional negative charge. Types of H bonds. There are two types of H bonds: intermolecular hydrogen bond 2. Intramolecular hydrogen bond. Intermolecular hydrogen bond. It is formed between two different molecules of the same or different compounds. For example, H bond in case of HF molecule, alcohol or water molecules, etc.